My name is Tarn Humphreys. I'm the Director of Business Development at Qube Technologies. Today we'll be running through quantification and localization using a continuous monitoring system. We'll talk about some of the challenges faced by the industry today in emissions reduction, run through how we are able to accurately quantify and localize, and talk about some of these case studies where we've seen success in doing just this. We know there are no shortage of challenges today for operators in this environment with emissions reduction. The regulations are increasing both at the federal and provincial level, involving methane reduction targets, greenhouse gas emissions reduction targets that are needing to be met. LDAR, or leak detection and repair, these are prescriptive requirements that operators are needing to adhere to meet regulations, as well as greenhouse gas related taxes that are coming into play. The energy industry is shifting. We've seen this shift in a move towards more ESG reporting, management, all the way through the value chain. Customers, stakeholders, investors are demanding this, and companies are required to have accurate reporting and management of their emissions. And in order to do that, they need this transparent and verifiable data. We know that gas emitted into the atmosphere is gas that cannot be sold, so there is value in retaining this product in the process and in the pipe for operators. I heard a stat earlier yesterday that quantified approximately $30 billion of lost product is actually being emitted into the atmosphere. So there's a lot of value in actually retaining this and repairing leaks, methane leaks specifically. Companies are moving towards certified gas programs, whether you call this independently certified gas, responsibly sourced gas. Companies are being paid premiums for responsibly sourcing their gas and being able to show that it comes from a responsible source. And one aspect of this is through monitoring and the monitoring programs that are associated with the process. We also know that companies are starting to see higher valuations and premiums as they have more stringent ESG, more transparent data, and just more ESG focus in general. We're starting to see this movement. Existing technologies in this space have their own limitations. They can be intermittent, they can be inaccurate, and they are often expensive. So let's dive into these three things. Some of the technologies available today for methane detection are intermittent, which means that you're only finding leaks when they are surveyed, not when they are occurring. This leads to many leaks that are being unreported and unmanaged, and that lost value into the atmosphere. Many technologies have their own inaccuracies, whether this be through drift, an inappropriate detection capability for the type of facility or application they are being used for, and or operational environmental challenges that they're not well suited for. And expensive. We know that operators are looking for a low-cost way, not only to be able to meet regulations, but to be able to showcase and really outperform in an ESG way for their emissions reduction strategies. The cost of surveys in the past has been prohibitively expensive to include a number of surveys throughout the year and or the scale that they're able to deploy at. So where we see a potential solution here is through continuous monitoring. So with continuous monitoring, you're finding leaks when they occur rather than when they are surveyed. And being able to detect 365 days per year, finding leaks very quickly, fixing them faster, keeping more product in your pipe. Shown here is an example of our continuous monitoring system. This is an easy to install system that's set up around the perimeter of a facility using fixed, low-cost sensors. Primarily, we're detecting methane. However, we have the ability to continuously monitor for other gases such as H2S, VOC, NO2, SO2, and CO, as well as adding capability later this year to monitor for CO2 and particulate matter. All of these are equipped with their own anemometer, so we're able to monitor individual environmental data such as temperature, pressure, humidity, wind direction, and wind speed. Each one of these is set up, and we understand that operators require a robust solution where it needs to be fully functional and with a high runtime over an entire season, 365 days per year. So we need a high temperature, high humidity, low humidity solution here. All of the data that we're collecting, both environmental and gas data, is sent via LTE to our cloud-based platform. And this is where we're truly doing the analytics here. This is where we can localize to an emission source and quantify how large of a leak is occurring. And the third component is a visual dashboard. Operators have the ability to visualize where leaks are occurring on their site and report and manage on a site level emission all the way up to a corporate level from a visual dashboard. This is all API enabled, so it can be tied in and integrated to other systems such as production, maintenance repair programs, other things like that. So what's the actual workflow here? Well, the first component is that detection piece of the environmental data, wind speed, wind direction, temperature, pressure, and humidity, as well as all the gas concentration data. We're monitoring this on a very consistent, continuous basis. The second piece is to localize, and we use a physics-based model to pinpoint an emission source, a likely emission source, and the consideration of having where that likely emitting equipment is on site. After we've done that localization, we can then use a Gaussian plume model and all the environmental data to put together what an actual calculated site rate emission would be. And we know that operators care about this rather than just a concentration level, but a site rate. How large is a leak that's occurring from a site? So how do we actually do this? How do we do this accurately, quantify and localize a leak on site? Well, the first step is that we require detection accuracy right at the sensor. So we use a low-cost metal oxide sensor for methane detection. These are off-the-shelf, highly sensitive to temperature and humidity. So each one of these sensors is required to have individual calibration where we're running it through a clean glass chamber subject to a number of temperature and humidity cycles. And we compare that input gas concentration, we calibrate, and then we compare that to our output concentration where you can see a match. And this gets us down to the resolution that we require in the less than 1 ppm range over a wide variety of temperature and humidity. So now we have a sensor that can accurately detect, but can it detect the size of leak that's occurring on the site at the distance you require? Well, this is this next step. And it's developing what we call our minimum detection limit. And in order to do this, we need a significant amount of data and controlled release tests to be able to generate this curve. And what this curve shows us is that we have a minimum detection limit on our technology of 0.2 kilograms per hour at a distance of 100 meters. And when we get up to a detection of 1 kilogram per hour, we have a 100% probability of detection. For reference, this size, this 1 kilogram per hour, is just over 1.25 MCF per day, so a very small leak. This enables us to accurately detect over 95% of statistical gas leaks that occur at any oil and gas facility. So one of the programs that we use to be able to generate this kind of data in a controlled release setting is through a program down in Colorado called METEC. This is an emissions testing center where technology providers are able to come in and have blinded daily controlled releases where they can validate not only their hardware performance, but the model performance of their localization and quantification as well. So this is an example, just one daily snapshot over a 15-week program where our system was able to successfully detect 2 events that came through, localize to the correct location, and quantify to within 20% of a known volume that was released. So we're using all of this data. We're using the environmental data, all of the gas concentration data. This is now where we're inferring that localization, where the leak's occurring, the quantification, how large it is, and a classification, whether it's a true vented emission or if it's an episodic known vented emission on site. So we would say that a picture is worth 1,000 words. We think a model is worth even more than this. So we've developed a simplified physics-based model here. What you're looking at is a top-down view on the left of a simulated gas plume in red. We've got some randomly generated wind data in the gray vectors, and you have a perimeter of 5 sensors around the outside. Sensor 2, highlighted in orange, is going to be focus, and the plot on the right is going to show that every time that plume of gas moves over the sensor 2 in orange, you're going to see a concentration spike happening. And you'll have concentration spikes happening across different ppm levels of gas. And it's not enough to just simply think about concentration. We want to know how that molecule of gas was traveling to hit that sensor at that concentration level. So we look backwards in time, and our system develops what we call an integral curve. And it's historically what a molecule of gas was doing from a point A to a point B to travel over that sensor in real time. So it's going to rewind that simulation, the same simulation. Now what's going to be shown on the right is this development of what we call these integral curves. And every time that gas plume moves over those sensors, it's going to draw this integral curve. And as we start to see these integral curves being drawn, they will have intersection points. And there'll be higher density of intersection points that correspond well to the leak location shown here, our plume in red. Now this is a very simplified model where it's just 5 sensors around the perimeter. So we know that within any oil and gas facility, there is going to be more complexity to this. There's going to be buildings, there's going to be topography, possibly more than one emission source. So the model does take all of this into account, and it assigns what we call a probability density function. So that if there's more than one leak occurring on the site, it's going to detect that and assign a likelihood of probability for one emission source or over the other. The continuous monitoring allows us to do this because we have all the individualized environmental data at each sensor, as well as the gas concentration data at each sensor as well. So now knowing how our localization works, we need to consider how we deploy and where we deploy on site, considering the likely emitting sources, as well as the prevailing wind. So in this case, this is an example of a site down in the Permian Basin. It has a southern prevailing wind, meaning the wind moves from the south to the north. We take a look and we map out the likely emitting sources, and we group them into asset areas on this site. Things like compressors, tanks, separators, flares, etc. And we map out and we provide a heat map and dispersion model of where that equipment likely would be emitting to, and we deploy accordingly. So in this case, we have 4 devices located around the perimeter, 3 on the downwind northern side of the facility, as well as 1 on the southern side. And this one device on the southern side allows us to generate what we call a site boundary and helps us to understand if it's truly an on-site emission versus an off-site emission. And that's critical when we start to think about quantification and how large of these leaks are occurring on site. Okay, so now we have devices deployed around the site. In this case, now we're going to show 4 devices in red, yellow, green, and blue. We have asset areas grouped into boxes. Now what are we actually doing? Well, we're measuring concentration and environmental data every 3 to 5 seconds. And we're calculating this every 5 minutes, looking backwards at the last 10 minutes of time. We then consider what's truly an on-site emission versus an off-site emission based on what the wind is doing at the time. And we're subtracting out anything from an off-site emission from our site rate total. So the model's doing all of this continuously. So with this example, we have a few concentration readings that come through on the west side of the plant on the blue and yellow sensors here. You can see those concentration spikes, much like we saw in the physics-based model with the plot on the right. Now we consider what was the wind doing at that time of those detection events. At the time of the detection, the wind was moving at approximately a 100-degree angle, and that means it was moving from the east to the west on the site. So if we think about where those likely emission sources are relative to the sensors, the arrows in green show that they could be coming from an on-site emission source, hitting those blue and yellow sensors. And the gray arrows show that it would be coming potentially from an off-site sources. So anything with the green arrows considered as part of the emission and a likely location, and the gray would be off-site and not a likely location. It's still detected, but not considered as part of this emission on site. Now we're actually localizing, and we take a look at the patterns of high and low concentration and compare that back to where the equipment is located and where the sensors are located on site. And we identify the regions with the high correlations. So anything up to a 1 is going to be the highest correlation and a strong indication of where a site leak is actually occurring. In this case, we can see this strong correlation is actually with the red asset area, or the treaters in this case, up on the northwest side of the site. As you have more than one sensor on location, this helps to improve the accuracy of these models because they're able to detect where high and low concentrations are and use all of that data accordingly. So now we have a likely known emission source. We have concentration data at each one of the sensors, and we can develop a Gaussian plume model that takes into account all of the environmental variability, the wind variability, wind speed, direction, temperature, pressure, and humidity, and puts all of this together to actually indicate where what a site rate would be from this leak. In this case, we can come down to it's approximately a 19 kilogram per hour leak that's coming from the treaters on this site. It's interesting to note here that you can't simply look at the concentration, because you could have instances where you had a very small leak, but low periods of wind, and you'd have a pooling effect, and therefore it would show an increased concentration correlating to a very small leak. And conversely, you could have a situation where you have a very large leak and high wind, and you're seeing a dilution effect. And so the sensors are going to pick up a very small concentration. So the model is actually accounting for all of this. And our model is also accounting for something that we call object permanence. And this is considering if you had a consistent leak source on a site and multiple sensors and high wind variability. So the wind's moving across multiple sensors and you're getting not consistent concentration readings at each of those sensors. The model is using AI and machine learning to understand that that is a consistent leak and it's causing inconsistent readings of gas concentrations at more than one sensor. So really this is where that AI component and that machine learning can help us to understand and be better informed as to what's happening on any given one of these sites. An example of this was a site that we had deployed continuous monitoring at. We had paired both a methane and a CO sensor concurrently in each one of these devices, and the operators were seeing alarms that were being triggered. We had set these up based on a particular volume and period of time. So if that was exceeded, the operator was receiving a site rate alert, and we were seeing about 15 of these in a month. We had localized to the treaters in this case, and they sent an OGI camera as a follow-up inspection to try and identify specifically where the leak was coming from, and they were not able to identify it with the OGI camera. We went back and looked at the pairing of both the methane and the CO concentrations, and we were able to determine that this was an example of incomplete combustion that was happening off the stack. They brought in a burner testing company to actually optimize and lean out the burners that were running rich in this case, showing incomplete combustion. And as a result of that, the burner conditions being adjusted, we were able to see a 90% reduction in emissions right after that burner was adjusted. So you can see on the left in the red, you just have that number, that emissions that are really coming through, and then the quieting down on the right once we've actually adjusted this. So the interesting thing to note here is that while OGI cameras are really capable in a lot of situations, this was one where specifically they weren't able to detect this because of the lack of temperature differential of that incomplete combustion coming off the stack. So just an example where continuous monitoring was able to help pinpoint that. Now they're able to use the same kind of procedure and optimize additional sites with the same kind of accuracy. We understand too that continuous monitoring and all these other kinds of methane monitoring, there's not a one silver bullet that's going to be applicable. We realize that there's going to be different applications for different sites, but this is just an example of where you can be pairing one or more technologies to help out. I'm going to jump here for a second just to a quick demo of how we're actually visualizing this. So on a site here, what we do is we can create a 3D twin of a site, and we can start to determine where these site emissions are actually occurring relative to the equipment. You can show a satellite imagery if it's available. In this case, it's not. But you can start to hover over these and really understand a heat map of where an emission source is coming from, what the wind is doing at any given time, and then start to include emissions by category if they're associated with a flare, a separator, compressor, tank, and really start to understand each one of these events as they're occurring in real time and having all of this data. And we understand as well that operators are wanting to know more than just an individual site. So we can take a look, it's not going to load here, but you can take a look on an overview page of having site levels by category across a number of different sites. It's going to be really hard to see here, but you can start to do bubble mapping. This helps companies do trend analysis of how they're doing, if they're making changes, how are these being improved over sites, are your emissions reductions increasing, decreasing, how are you compared to some targets? and just how you're doing as an asset level or a corporate level as well. Just one more success story that we talk about. This is more local to Alberta. This was an Alberta site that we had included continuous monitoring at. The operator was receiving leak notifications over a period of time. We were able to localize methane leaks to the tanks located with the red X. They were able to identify there was a leaking thief hatch, repair that leaking thief hatch, and bring the baseline levels back down to normal on the green in the plot up to the right. It's interesting to note here that this is a site that would have typically had an annual LDAR survey with an OGI camera, but we were able to find something within days, repair it, and bring it back down to normal. The alternative to this would have been this leak might have been going for almost a year prior to it being detected. So just an example where that continuous monitoring piece was really able to help an operator identify quickly, remediate, and bring that back down to baseline. We feel that continuous monitoring allows companies to have actionable insights at a fraction of the cost. And the implementation of continuous monitoring combined with all the advances in AI and machine learning allow us to be able to actually quantify and localize greenhouse gases and be able to keep more of this product in the pipe for operators. Thank you very much. I'm happy to answer any questions.